Here we are with part 2 of day 14 of Advent of Code 2020. In this part, we realized that we actually need to be working with version 2 of the chip decoder. And the way that version 2 works is that instead of applying this sort of strange bit mask to all of the values before we put them into the memory slots, we actually take the value as is and we put it into a memory location that has sort of a new set of bit masking rules applied to it. So these rules are: if it's a 0, the corresponding memory address bit stays unchanged. If it's 1, it's overwritten with 1. And then where it gets really interesting is if it's X, then that corresponds to a floating value. So we can see here that with the 0, 0 stays unchanged, 0 stays unchanged. The 1 becomes a 1, but it's these X's that are floating spots. And what it means that they can float is that they can be either a 0 or 1. So we have to apply, we have to generate all combinations of memory addresses that these floating bits correspond to, and we have to set our given value. So for memory 42, value 100, we have to set that value for 100 in all 4 of these memory slots. Similarly with this masking in 1, we have 3 X's, which means that 1 will have to go in 8 different registers. So we keep track of the memory values in the same way, and eventually we sum them all up and we get some sort of answer, which is the answer to our puzzle. So let's start with, this is our input, and we'll work towards 208, and then we'll see if we can take on the full input after that. So I'll create a sample 2, which will be that, and then we'll open part 1, and I'm going to save that as part 2 because I think we'll be able to reuse some of this. Yes, so we'll have memory. I think some of this masking will be the same. This is going to change the apply bit mask, so we'll have to rethink that, comment that out. All of our parsing is fortunately going to stay the same. Yeah, so if we have a mask, we apply it. I think because it's saying, well, I don't even know if we want to do the bitwise masking this time. I think we might be better off approaching it a little bit differently. So I'll comment those out. I still want to set the mask if that's what's coming in. But yeah, we get down here, we match our memory, we extract the value out, and instead of masking the value, we want to get all masked memory locations. So I get masked memory locations based on the memory location and the current mask. And then once we have that, we can iterate over our memory locations. And we can stick the actual value into each of those locations. So that's sort of the structure of our program, and it's this function method here that's where we're going to be spending most of our time. So let's see if we jump over to the sample. We come back. Just want to have something to I have something to reference. And yeah, so in the case of this, all the zeros get ignored. If there are any ones, they would carry through as ones, and then these x's become the floating bits. So what I'm wanting to do is take the memory location, turn it into a binary string, and then right justify it with, I guess, 36 zeros. I just want to make sure we always have a string that's padded on the left with zeros. And yeah, so that'll be our location as a binary string, I guess. Sort of a long variable name, but hopefully it'll help us. And then we want to, yeah, let me grab this and maybe we can just work this out. So we'll think about this in pry for a second. So we'll say our mask is this and our memory location is 26. So if we apply that same thing to string, we get that, but if we are justify it 36 and that dot side, yeah, that's 36, good. So if we take the mask, and what I want to do is go through this mask, and I want to, maybe we'll actually update this mask to give ourselves a 1 in here somewhere. So let's say that. And so I want to take the mask and split it up. That way we can, so split it up and we can map over each of those values. Yeah, what if we were to split it and then zip it with, what was it called? I already forgot the memory location. I think I didn't set it to anything. MLB, memory location binary. Okay, so we'll say mask.split.zip with MLB.split. I think we just get all these, yeah, values lined up. So then we could iterate over that. So we have the mask value, we have the memory location value, and so if, yeah, I think if mask value is equals 0, then we want to return the memory location value, because anytime there's a 0, we'll just take what's over here. Otherwise, if it's an x or a 1, we want to keep the x or the 1. So we'll keep the memory value. Yeah. Okay, so we get a string of zeros, 1, and then x's. And so given our mask and given our MLB, does that look right? Yeah, we have 1, 0, 1, 1, 0, 1. Then we have x, 0, xx. Okay. So I like this equation for producing, and we can join that all together. this thing, which gets our 1s and our x's in. And I think we can go from there and like interpolate in some different values, because now what I'm thinking is, so if we have 3 x's, you know, if we say mask dot split dot I wonder, does count take a block? Count where the capital X. Yeah, 3. So, you know, if we can do something like that, and then we count 3, then we can say, you know, 2 to the third is 8. And 2 to the third minus 1 down to 0 is going to be an array of those values, which we can then map into binary. Yeah. Like that, we get, you know, all these different binary values, which happen to be all combinations of values that we need to inject into the x's here. So we can adjust that to 3, because this is 3, with 0's padding. So this gives us kind of all combinations of values that we'd inject into these x spots, which we could then use to generate our different memory location strings. So if I call this, I don't know, combos, some terrible variable name for now. So if I say combos dot map, and then, yeah, where was our join? This thing. So we take that thing and we sub out all of the x's for these like formatting strings. So if I insert these, then you can format in some other value. And I'll use the formatting operator with combo.split. And I think that's all good. I just got to close that. And yeah, we create 1, 2, 3, 4, 5, 6, 7, 8. And I think we're getting all combinations of those values in there. So yeah, I think we're onto something, but I want to copy some of this into our session so that I don't lose it. Yeah. I'm going to comment all this out, but we'll just have it for reference. So we have this string, we have our mask, and so that's where this is going to come in. So this is our mask with floats, I guess. That's what those x's are. It's going to get this, and MLB needs to be location, a binary string. So that's going to be our mask with floats. And then if we are to count up, then we'll say the x count is that. Yeah, I'll put that up here. Then yeah, then we can grab all our combos, these things, and then instead of 3, we'll say x count, and instead of 3, we'll say x count. So that's going to give us all the combinations that we need to produce. And then lastly, yeah, we'll run this. Except this value in here is going to be our mask with floats. So yeah, this is going to produce our locations, strings, I guess. How do we want to store them? I guess we could store them like that. They'll all be unique. That's fine. We'll return locations as strings. And so now we have this get masked memory locations function. Are we calling that? Yeah. So we'll get all the memory locations, we'll jam those values in for each of those, and then at the end we'll pull them all out and sum them. So do we get 208 for our sample input? Get masked memory locations to S on line 19. Oh, sure. Yep. Did this in the previous example as well. Memory location comes in as a string when we parse it out, so then it needs to be turned to an integer. And plus, string can't be coarse into integer, so where are we doing that? Line 69. Oh, the exact same thing. We need to turn those into integers as well. And now we're getting 208. I feel good about that. Let's jump to our input. Took a second to run and it produced a big number, so I'm feeling pretty positive about this. Let's see. Awesome. We got our second gold star for the day. That was a doozy of a problem, but we got through. Anyway, thanks for watching.